We've talked about stochastic gradient descent. It's a workhorse and it will eventually get you to the right solution. But if you look at a lot of the toolkits that we use for deep learning, it's not the default. Things like AdamW are. So what we're going to talk about today are some of the problems with SGD and how things like AdamW deal with them. And as before, I'll use my analogy of walking to Union Station. Batch gradient optimization would be sending a survey to every person in the DMV to figure out where to go. SGD is asking a couple of people which way you should go. The first problem with SGD is isotropy. SGD treats all dimensions as the same. This isn't great if the gradient is big in one dimension and small in another. You end up crawling along the shallow dimension and jittering along the bigger dimension. Now, you can do things in SGD to deal with this, like making sure all of your inputs are mean zero with unit variance, but particularly with deeper models, this can still be a problem. In the Union Station example, if you're 10 kilometers east and 566 meters north, you can bounce back and forth between Maryland and Virginia, but take forever to get from K Street to F Street. The second problem is if there are local minima or saddle points. These are points where the gradient is zero. If the gradient is actually zero, the optimizer will stop. I'm not sure if this actually works for my Union Station example, but let's say you're on the metro and you ask which direction Union Station is, you'll get gradients that have a local optimum at the metro station for Union Station. But a better fit is the actual Union Station where you can get on a MARC train or an Amtrak train or a VRE or something like that. Mathematically, the classic saddle function is x squared minus y squared. If you take the gradient 2x and 2y, it has zero gradient at the origin, but that's obviously not the highest or lowest value you can find. You can go up the front or down the side. Finally, SGD can be noisy. You're taking a gradient with just a few samples. So you can inadvertently go in the wrong direction. Going back to our Union Station example, you've been going northeast, 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 and then you talk to some people who confuse Union Station and Union Market, and then you start heading southeast. If you could have some way of remembering that, hey, it seemed like Union Station was in this direction, you could remember and not go off course so easily. So how can we fix these things? AdamW combines two things, momentum and RMS prop. Momentum is often attributed to On the Importance of Initialization and Momentum in Deep Learning from Sutskever et al. And this basically says that if everybody says you have to go west by northwest to get to Union Station, some bozo telling you to turn around is not going to change your mind immediately. Mathematically, this adds a velocity term, a running average of all of your previous moves that keeps you moving in the same direction, even if you hit a local optimum or a saddle point. The other ingredient comes from not viewing all dimensions as the same. The first optimizer that I learned about that did this was AdamW from Ducci et al., but AdamW using RMS prop from Tillemann and Hinton is perhaps a little better known today. This scales the gradient based on the sum of squares in each dimension. This is something called per parameter learning rates or adaptive learning rates. So let's take a look at AdamW in pseudocode. We're going to see something called moments. This comes from statistics, and it's the expectation of x to the n. So the first moment is the mean, the second moment is the variance, and these correspond to momentum for the first moment and RMS prop for the second moment. But there's a problem here. Both of these start at 0, so you need to add a correction to account for the fact that both of these moments are going to be too small at the start. And there you have AdamW from Kingma and Ba, but that's not what you always get in your favorite optimizer code. You often see AdamW, where the W stands for weight decay. Now, for most of the papers that I've talked about, the story is that somebody comes up with the idea, it gets published, and then that's what gets implemented. AdamW from Loshkilov and Hutter is kind of the exception to that. It got released in 2017. I'm going to read this comment from its review in 2019 verbatim, long after it had been shown to work and was adopted widely. Evaluating this paper is somewhat awkward because it has already been through multiple reviewing cycles, and in the meantime, the trick has already become widely adopted and inspired interesting follow-up work. Much of the paper is devoted to reviewing this follow-up work. I think it's clearly time for this to be made part of the published literature. This was after it got rejected a bunch of times. But anyway, the idea of AdamW is that they thought the implementation of Adam was wrong. Many people take the shortcut of just shrinking weights and calling it L2 regularization of the parameters. For vanilla SGD, that's exactly the same thing. It's equivalent. But if you add momentum, it ain't equivalent anymore. The argument of AdamW is that you should just do weight decay and not L2 regularization. And history has vindicated this argument, although the reviewers in 2017 and 2018 weren't impressed by the theoretical arguments. So now when you see Adam or AdamW as your default optimizer, you'll know why it's called that and what it's doing. Thanks for watching this video. I picked out another video that you could watch up here. If you want to get more context for the videos, check out this link or the link in the description. It gives you readings, programming assignments, and other things that might be more helpful. Finally, help me out and help other people find this content by providing a big gradient to the recommendation algorithm. Like the video, subscribe, or leave a comment down below with mistakes that I've made, newer research that has come out, or just tell me about where you are in your journey.